Okay, we're doing transformers. Let's get into it, bro. So let me copy paste this. I'm pretty sure, bro. Let's see the shiz. Na, 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 na. Okay, this is transformers. Okay, we have hello, I love you, tokenization, embedding, composition, encoding, multi-attention, add a layer norm. Then it should go somewhere else, bro. Where is that? Okay, gain previous similarity, attention weighted mean map, weight to info values. Like just and then map it into info values. And then this is encoder decoder network, then tokenization, position encoding, mass multi attention, earlier norm. And they have interconnections between different modules, interconnected modules. So it goes to attention wall and to the layer norm, and each one goes to this one also. Then linear format. So we will like try to implement the transformers attention already from scratch using PyTorch. Basically, transformers have an encoded decode architecture. This is common for language translation models. What is common? Encoded decoder. Okay, they are gonna. I mean, I don't know if I'm just copying, working through it. But let's see. Here we are not going to be in in-depth installation transformers. This one blog. Okay, there's a blog, and then we can do that, bro. So let's get it. Okay, so we have encoder, decoder. So let's just build it. So let's first install Torch Text. Quick to install Torch Text. Oh shit, I haven't even connected to runtime, dude. GPU, come on, bro. GPU. Yeah, we got a GPU. Fuck, let's go. So let's import the packages. Import Torch. Yeah, now we need import Torch, obviously. Import Torch. Then what else do we need? Import function. Okay, that I don't know what that is, but let's see what that is. Import Torch dot function as f. Import math and copy and okay from copying models. Import math, copy, and what else do we need? Okay, rejects also, and then import warnings because you want to suppress warnings. Come on, bro, take the time. Import warnings and import pandas as PD. You know what's common? Wait, let's see. What is common between poachers in China and data scientists? Poachers import pandas as PD. So this is the import is common between poachers in China and data scientists. Answers import pandas. Ahora speaking about all import number as NP and then import Seaborn. Bro, who uses Seaborn, bro? I mean, I know that's damn, it's really meta now, but import, we always have touch text and import now there we go. Not for live dot and DLT boys. Oh, warning, simple filter on warnings. Simple filter. Hmm. About to. So let's go to the basic components. So, uh, So now we're going into the basic components. Give up. Let's see what's happening on the chat, boys. Oh, no one's on the chat. What's happening in the chat? Damn. What's in it? The stream. Right on. Channel trans. Okay, first let's go to the basic components. First we have to create word embeddings. What is this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, there has to be 7 though. 1, 2, 3, 4, 5, 6. Okay, let's get word embedding. Guys, bro. Oh shit, the max is 6, huh? Shit. So we have to convert each word. So let's see how we can do that. First of all, we need to convert. So something. Let's just, I'll give you an idea, bro. So first of all, we need to convert each word in the input sequence to an embedding vector. Embedding vectors will create a more semantic representation of the word. Okay, so we need to create probably dimension 5 and 12, okay, and then we have a vocab size of 10. Then our embedding matrix will be of size 100 rows into 512 columns. Huh? Oh yeah, each word, because actually our embedding matrix, yeah, will have that because there's that many rows, so that many possible words, and 512 is in each dimension what it means. These matrices will be learned on during training during inference, and each word will be mapped to a corresponding 512 dimensional vector. So we have 32 of sequence of 10 words, then the output will be a 32 byte size and 10 rows. That means 10 words into 512. So let's see how we can do that. So let's say we have 1, 2, 0 list of lists. Then X, why are we doing NP array? We can just to torch tensor, but what is the point of this? 0, 1, 0, and then we have another 1, 0, 0. But I'm just copy pasting this for one last time. Okay, and then weights also. So what? three rows into three dimensions. No, three rows, 3 cross 2, and then just print this shape, dude. One is three, and one is 3 2, one is 3 3. Okay, and then we can just do matrix transform. So we get that. Okay, cool. So now let's actually define a class of embeddings, and this is actually our embedding, which is inherits from for the NN module. No? Class embedding imports from dot module, and then we put, okay, first we initialize it. Bro. Self, okay, we give it a vocab size, okay, embedding matrix and embed dimension. Usually someone uses 762, but okay, fine, they're using 512. And then we call it super, give it the embedding class itself, and then we initialize it with all the parameters that actually matter, which we're too stupid to do. And then we just put self.embed, create attribute embed, which is basically a module dot, I mean, NN, what is NN, bro? I forgot that. Neural network embedding with the vocab size and number dimension. Basically, yeah, I think what is this? Vocab size, then def. Bro, I want to use GPU, bro. I'm not being selfish. Let me use it. Give me some time. Def forward, and then you put self, comma x, and then what do you do? Okay, we just not under. Let me just put on now. Then I think that's probably it, bro. So it's a very simple class. We have embeddings. We get input self and the vocab size of how many possible words are there, and embed dimension, and then we call the super class and the class itself and itself. I don't understand this part though. I'm not sure what this means. Usually you just send self, but I don't know why they're sending embedding also. And then you initialize the class, and then you create attribute, which is basically an embedding layer with the vocab size and embed dimension. So the shape is basically vocab cross embed. Done. Okay, and then I just whatever output it gets x and multiplies this into that, and it's done with. But usually there's a lot more to do. So let's see next what we do. 1 2 3 4 5 6. Position encoding. Now what we do is position encoding. I'll just copy these to all this. That's pretty decent information here. So we can just do that. So basically, we need to generate position encoding. So order to make sense. I'm also learning with you guys, bro. I have no clue. Let's see. It needs to know two things about each word. What does this word mean? What is the position of the word in respect to the sentence? In attention or in paper, they ought to use the following. I think you sign cosine function. Cosine function is used, and even time steps or time steps cosine function, even time steps sine function. So 2i, 2 plus 1 is odd, this is even. So position encoding will sine into whatever that position is, divide by 1000, raised to the power 2i by dm mod. Same thing, position by 1000 raised to 2i by dimension of the model. Position reference the order in the sentence or basically in the row. Reference to the, oh okay, position along the embedding vector diagrams. Position embeddings will generate a matrix of similar embedding matrix. So positional embedding will generate a matrix similar to the embedding matrix. It will create a matrix of dimension of sequence length cross embedding dimension. For each token or word in sequence, we will find the embedding vector, which is 1 cross 5.2. So one row of 512, and then it is added to the corresponding positional vector, which should dimensions 1. Okay, we will create the embedding vector also, and then corresponding position vector of that also 1 plus 1, and get 1 cross 512 of each word. For example, we have a batch size of 32, sequence length 10, and embedding. We'll have an embedding vector dimension this. So we will also have a positional encoding, and then we'll add both, like just combine like a stack. Okay, not stack. You don't. That's not what you do. You add it element wise, I think, and then you get it. Okay, so let's get into that. I think there's a Medium article also. Where's the Medium article? Oh no, it's just so basically it basically learns the identity function. I think it's here. So let's just put this in here. So x comes in some this thing, some this thing, and h of x. This h of x is actually the identity. They basically have to be the same thing. So this is embedding f of x value. So h of x, this is h of x is equal to this f of x plus x. That's it. Deeper version of shallow network will be found by learning identity transformation. Deeper version of a shallow network would be just fine by learning the identity transformation in the new layers. The identity connection from the input allows resonate. Okay, we're doing image here. Okay, I don't know. We'll see. I read on a copy of that input. Using this idea, we will train really deep networks. So let's see that. Register buffer and PyTorch. If you have parameters in your model, which should save and restore them in static, but not trained by the automate. Okay, I don't know. The instructor is given some instructions. What is that? Register buffer and PyTorch. Okay, I don't know what that means. If you have parameters in your model, which should be saved and restored in static. Okay, okay, this saving. Not trained by them, you should register them as buffers. Okay, okay. For saving and loading models, you save them in static and load the model from the state dictionary. Okay, but then you should register them as buffers so that they're not trained by the optimizer. And what is not trained by the optimizer? Wow, embedding matrix also is trained by them. I don't know what you won't train by the optimizer. Dude. Everything is trainable, no? Every layer, so I don't know what we'll see. Okay, let's create a positional embedding. Imports from neural net mn.module. And then so we initialize the matrix, that's the one too. Then we call the superclass, is in the positional embedding class and self-initialize it. In self.m.dimension, we just create an attribute embed dimension and embed model dimension. Then we create a positional encoding of torch zeros, max sequence length, that is actually acceptable. That's context length of the model probably, and then self.embed. Okay, the number of rows and the number of this thing. Then for each position range of max sequence length for each row, and for I in each range. That means pi, okay. P pos I equals method sign position, and P pos I equal. And for this thing, and then you unsqueeze it. So you basically just populate it with some position, and then you register. Okay, and this is the positional encodings. Okay, cool. So we can actually take a look at it in detail and see what that is. So let's get into it, okay? So first we put super positional embedding some self, and then we initialize it, and then we create a self dot embed. Oh shit, I didn't create a class for it. Def embed dimension, embed model dimension, okay. And then max sequence length, sequence length. I think yeah, embed nothing goes together. And then we put self dot embed dimension. This is same as the model dimension because you're adding it, right? I mean, you all get it right now. That's it. Embed model dimension. And then we put position encoding. We create torch of zeros. And what is the shape of it? Max sequence length, that is the number of rows, and self dot embed embed m. Come on. You're never supposed to do this for a suppose handle by the keyboard. Then cool. So now I'm pretty sure there's a more better way to do this, but I think we're doing for loops. Maybe once I finish my dynamic programming course and my algorithmic course, I do proper revision, you can do it. So for each row basically. Wait, let me just so got the yeah, no, you don't need this. Okay, so let's see what this is. Okay. Say we create max is equal to probably 100 and we put on the dimension. So 762 we put 40. Okay, got. I mean it is very common. So for each row we can actually make a so for position in that and this thing we just go. I mean this is so unnecessary bro, but okay, let's see. For I in range of a, let me just get that picture. So basically this, okay. So for I, yeah, I'm using 1 minute. Okay, let's see bro. Device equals torch. I don't know, the CUDA. Shit, how do you do that? Fuck, what is that? Get device. Yeah, I have it somewhere on top. Mm. What is it? Torch.cuda is available. CUDA, okay, device. And device equals fish, bro. I forgot it again. I forgot it. Fish. Okay, X dot. So just put some random. Okay, I'll put some. Okay, X dot. Because it's so unnecessary. You do it once, you don't remember it. Uh, A equals torch dot prime. Dot to. I mean, it's damn cheeky, bro. But I just need it. Let me finish this. Getting a GPU later is very hard. Let's see. Then, man, I don't feel good scamming the GPU, but I'm pretty sure they have a lot. Fine range of. Screwed, bro. I don't feel good. But then I have to run everything. Okay, I can run it later. Okay, let's see for I in range of whatever. Uh, embed dimension, embed, embed model. Okay, then see this is the function. So this is the most important part. You can just look down. Okay, see position, comma I. Oh, we have to do this right too. Okay, so 2I, right? So this will be odd or even. First will be even, then one will you put I plus one. So basically equals math dot sign. And then what is that? Position by 1000 or 10,000 to the power 2. Okay, and what is I? Into I, whichever position that is basically the range. And then divide by 7 is about embed dimension. What should we do? We don't do this with no. It does something like okay, and then that basically is that. So 1000 raised to the power 2I divided by dimension of the mod. The whole thing basically. This is the denominator. 1000 raised to 12. And now same thing. But here we put I plus 1, I plus 1. And here we put cos. It's basically the same thing happening. Wait, why is there a mixed match of I plus 1? Then what do you do? PE equals P dot 1 is 0. 12 dot register. You're putting it into buffer. Okay. Oh, this is non-trainable. Okay, this is non-trainable. Position encoding are kind of fixed. Okay. So this is why you put it in. You don't train this. Yeah, parameter model should be saved and restored in state but not trainable by the outcomes. Okay, when you save the model, it will be stored in, but they're not trainable by the outcomes. Okay, cool. So def, this is in the same line. Def forward. I'm pretty sure you just what do you say, x equals x whatever into dot sqrt sqrt right, and then done and sequence one equals 1. Okay, I look at the that's I will check all that out. X plus dot dot autograph dot variable. Okay, this is all new to me, dude. I have no clue what this is. All sequences, full sequence length. Okay, now I'm fully confused, bro. Requires grad equals false. Okay, I am fully confused, but we can work through it, bro. Embedding diamond number of heads in circle. Okay, I have no clue what's happening. So we get a matrix, we get a input. Okay, we then that same thing we do element wise for self dot embed dimension. That makes no sense. Math dot square root self dot embed dimension. Okay, so for each x in that whatever, we multiply it into the square root of that. Okay, and then we get the size of it, which is the same almost, which is the same. And then we add that autograd variable self p. Okay, we do autograd of that variable with respect to some variable self p from and then I have no clue what this is, bro. We'll have to see that later. Okay, let's go to self attention, bro. Okay, let's just work it out first. Yes, let's do this. Why is this thing up? Oh man, that was a proper error. I wouldn't have caught it also. Wow. That's what you don't understand what happens. This will be what? Will be shaped like that only, no? For 1040. Well, let's see what is that now. So okay, you put it for batch size, each batch size. So individual position embedding for each one you create and we'll get it. Okay, that's easy. Oh, okay, now I understood it. Okay, now I understand the sequence length, but because it's already one right, so this is actually a sequence length. How much our sequence length is? Sequence, okay, what is this do, bro? What is this actually? Let's go to touch. Yo, oh, cool. Ah, bro, what is variable? Okay, that's autograph. Hmm. Bro, what does autograph just do, bro? With respect to what it creates? Gradients should be computed. So just creates with respect to what though? I'm not sure. I mean, with respect to okay, position encodings, I guess I'm not sure. What does it create? Create. Okay, let's see this. Chat GPT, bro. I hope my chats are not exposed, bro. Oh shit. My chats are exposed. Nice. Okay, this creates a variable for the autograd. Okay. So what is dot from autograd? Okay, so okay, we're just but detaching. Okay, cool. So we're just adding the position and coding, bro. That's it, dude. Shit. Oh, that's so much drama. Okay, cool. Ah, it's all that in my head, but I just don't remember it. It's like, okay, let's see what we're doing. Now we're doing self-attention, bro. Bro, this much I have to do. I'll show you wait how much I have to do. I have to do this much. Okay, and all of the code we have to do freaking diffusion models and then UNet for diffusion models and then what is that? GAN also and data loaders also. How much, bro, we have to do? I mean, I already knew a little bit of it, so for me it's not that bad. But I don't know for other people, bro. Like, what the fudge? How much are you going to study? I'll tell you what now is self-attention and encoder decoder, testing and useful resources. Then BERT and GPT, vision transformer, BERT and GPT, then vision transformer, diffusion model. I don't think we have diffusion model though. And then data set, data loader, then GAN, generator ladder cell networks. Bro, what the F, bro? It's like, man. I mean, I won't do This button, I think I'll do button GB. I want to vision transformer. Oh, I have to. Shiz. Okay, we'll see. We'll see. I'll see if I have time. I'll go through it. So now I arrive self attention. Okay, let's see what self attention. Let me give you a glimpse of self attention. Okay, sir, give me. What is self attention? We have a dog is crossing street, but it never because it saw the picture. What does it refer to you? What does it refer to you? Come on, man. You gotta. Dog is okay, that's also dog. And for disease, understand it's humans. For humans, but for machines, it's not. So we need self attention to actually see what we're referring to as objects, subjects, blah blah blah. So each model processes. Now look at other positions of the input sequence of so it creates a vector based on dependent on each one. Okay, that's pretty decent explanation. So let us go through step-step illustration. For fun, calculating the self-attention is to create three vectors and then code as input vectors. In this case, the embedding of each word, three vectors. So we need query, key, and dimension. So we'll see that. For each word, we create a query vector, a key vector, or a value vector. And you also use D, but that's you don't get it. Each of the vector will be a dimension 1 to 64. Why, bro? What is okay, we have embedding dimension 5 into. Since you have multi attention, we allow 8 attention. It's go to theater attention heads and how queries and queries are. We allow query many matrix, query matrix, and a value matrix generate query, key, and value. These matrix alone during training. So code hint. Suppose you have a batch sequence and embedding dimension. So after embedding and position encoding, okay, your dimension 32, 10, 5, 12. Cool. We will resize this into 32, 10, 8 into 16. So 8 number of heads in the attention. And don't worry, you will get to know what responsibility will look. Okay. Thank you, sir. Second chapter is calculate the scope. QK into creative. Code in. Suppose a key query and value dimension. Key query and value dimension will be this. Okay, 32, 10, 8, 64, 8, 16. Okay, so this they just changed it to how much ever is suited for y'all. So before proceeding, we will transpose each of them for multiplication convenience. 32, 8, 10, 64. 32, 10, 8, 64. So this 8 and 10 would be outside, so 8 count, 10 goes outside. Okay, so 32 into 8, 32 batch size and 8 attention here will do it. Then what is 64? That 8 is coming from 64, so you want to put querying transpose. So 32, 8, 10, 64 is the resize matrix into 32, 8. Or would we get 32? Okay, so each of this 32, that doesn't matter. So 8, 10, 64, 8, 64 into 10. What the fudge? 32 by side, multi attention and never changes. Okay, 10, 64 and 64, 10. So we multiply each 10, 64, 64 plus 10, 8 times for one set, and then 32 times for back size. Okay, cool, bro. Damn, bro. I'm telling you, it's just freaking shapes, bro. It's at high level shapes. Did spit on my key? Okay. Now we divide our matrix in the square root dimension of the key matrix and so on. Define 32 8 vector by 8 square root is the dimension of the key matrix. This will get multiplied by matrix. After step 3, output dimensions 8, 32, 8, and then okay, and by 8 the square root. What's that? Divide. I don't know, element wise, and probably. No, you multiply this with the wire matrix. 32, 8, 32, 8, 10, 64, 10, 10, so 10, 10 into 10, 64. Output dimensions are 10 is sequence. So for each word, you have 64 dimensions. We pass through a linear. Again, we transport it back inside, and then we transport it back to our path linear. Thank you, bro. Thank you, sorry. Pretty good explanation. That was pretty good explanation. I'm not gonna lie. That was damn good. That was bomb. That was bomb explanation. I actually understood it for the first time in my life. Before I just had like a superficial understanding to have conversation. Now I actually understood it. Because I saw the matrix, I understood what the conceptually what it was. But practically now only I understood. And that's pretty good explanation. Like probably how many like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 10 code cells, bro. He explained it. He explained it. That's pretty good. I don't know if I have viewers, bro. Let's see. I have zero viewers. Zero viewers. I have zero viewers. Bro, I'm damn fucking lame. Don't swear, bro. Myself and we have embed. Okay, finally get 5,000. That's decent. And then that's equal to 8. So this should basically be what do you say, HCF? Not HCF, a factor of this. So you can actually factorize this. I'm pretty sure. I mean, that's basic, man. You can actually use this as hyperparameter. We'll see later. I mean, from my this thing, but we'll see. Multi. But what's self-attention? But this is multi-attention or self-attention. Okay, self-attention is used by positional encoding, and multi-attention is using this. Okay. Multi self-attention, I think. I'm not sure, but I have no clue. Let's see. Embed dimension. Um, but I'm not listening to the same songs you're all listening to. I'm listening to German songs. Yeah, I'll show you which songs. Yeah, this. Where am I, bro? Yeah, I'm listening to this because it's if I listen to actual English songs, no, it's not gonna help you. Like I'll just be singing the song. But this I don't understand the words, and it's pretty good. I think German is banger. Spanish is a little bit too banger, so you don't concentrate. This is more techno, so it's like very decent. Number of heads. I mean, I've got zero head, bro, till now, so that's kind of sad. I mean, not really, but पसंद आ रहा किसी भी नहीं है भाई. Hmm. So we have self-embed dimension, number of heads, single head dimension, and what is that? We shall see. That is basically a self-embed, which is 512. No. Okay, cool. So So now we actually come to the crux of, I mean, the secret sauce of transformers, bro. The key query and value matrices. So let's see that. So for query matrix is running not linear and self dot single dimension. So query matrix is basically a linear layer. Oh, okay, hit a linear. I mean a matrix with single head dimension. That's probably what 64 and 64. Okay, so 64 plus 64. Bias equals false, and then we have self dot key matrix. I think it's also the same. You know, self dot single dimension, self dot single dimension, bro. Um, so okay, we don't have any bias for each of these. I wonder why. Let's ask ChatGPT. Why do we not have bias for attention layers? Attention layers. Multi-head attention layers. The drive and query matrices. Multi-head diligent just like the most down. So okay, this is a formula. Go to the dot product. Okay, yeah, so then having that's so stupid, Brian. Of course, they go through dot product. User doesn't comment the list. That just goes to the right side. Like, yeah, that's not even know. I should try this. What an idiot I am, bro. How do I not even think? I mean, I knew it, but I never thought about it. And then they give the parameters. So WQ. So yeah, so that's why we don't have that. But actually, doesn't matter because it's all self dot products, you know. How did I not know that shit? But actually, I never actually thought of it till now because I'm a live stream now, so more self-conscious to be perfect. And that's actually terrible. Single head dimension. So, so dot out equals and then the linear so dot head. Okay, this is what is a reshaping almost reshape layer self heads. So it's basically 8 into 64 single dimension. Okay, and self double. So basically, how you get it here only, you know. That is really. I mean, I understand it. Maybe 60%, bro. So key query value and mass equivalent, obviously. So let's see what this is. We have a key vector, query vector, and value vector, and mask for the decoder. And it returns, what does it return? An output vector from the multi-head. So let's go ahead with that. So we have a key. Batch size is the first dimension. So this is basically the input itself. I don't know why this is a key. Sequence length, key dot size from query dimension can change in decode during inference, so we can't take general sequence length, yeah, obviously. So sequence length of the query. I have no clue what query and key is, honestly, right now. Sequence length. So I have such a supervision view now. Actually working it out helps me understand it. Okay, so we have the query size so that we don't mess up our query dot size. So now the disruptor is given us first by one column. Okay, so let's go ahead and create the key matrix, which is equal to, I don't know what key dot view is. Key dot view flat size sequence length. Okay, self dot. Okay, let's actually go through the code and then we can write it. So we have a key dot view. What is key, bro? Torch dot view. Let's see what torch dot view is. Torch dot console. I think it must be. Okay. Oh, okay, cool. So this basically for more efficiency, bro. It's the same data like in backend, but we just basically reshape it to some extent. That's the idea like this for efficiency purposes. Okay, it's basically like a reshape. Cool, cool, cool. So then the gradient also, no, but we don't calculate gradient. Okay, then we reshape it. That's awesome. And then we have key matrix. And we transpose it different dimensions. So we create a different shape. And then we transpose that shape also. And then we send it to each self dot key matrix and to each of the dimensions. Okay, and then we get the Q. Then we transpose the required dimension. And then we actually do some other stuff, and then we just do basic math multiplication. And then if we have a mask, we fill it up with the mask to a very 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 low value so that it actually gives no significant response. And then we divide it by the square root, the dot top product by the square root, I mean div up from the dimension end. And then we apply f dot, okay, a functional dot softmax across the dimension minus one, that's last dimension. And then we multiply those softmax scores with the values. And then we concat the scores transposed. Okay, that's damn crazy. Oh, 7.7. No, no, I'm talking about default. Oof. Whoa, where's your farm? No way of the town. So let's go ahead and create a view. It's all in the forward button.
So so basically we have batch size, sequence, self dot in heads and self dot single head dimension. So basically this three, I mean let's see that. This is what happens, right? If I'm not mistaken. But what is query? But yeah, yeah, okay. But what is the key query and value that gets reshaped in attention layers? If we need transformations from what is that? Inputs after positional encoding. Is that here? See, now we have this. Yeah.
Yeah, but what is the input? Okay, all the input layers go through different matrices, so we just name them different shit, but it's all from the same X. Cool.
That's what I had it on. Now I think is nothing else to do. Query equals query dot view. This is kind of simple. The batch size is always the same. Sequence length is always the same. And now this whatever the embed dimension, we put it self dot and heads and self single dimension. Mm. Yo, why, bro? What, bro? Come on. Yeah, not text. So I'm just checking if it's there. So what is the this thing? Torch text. Some torch text input vocabulary. Okay, we can try that. Some torch text. Import. Okay. Okay, I don't know how that is. I tried it some big brain shit, it didn't work. Okay, okay. Key also same thing. Key dot new, batch size, the same. Sequence length is the same. And self dot in number of heads, it will basically divide the output because I don't know. I don't have any mathematical underlying understanding of why they do it, but I'm pretty sure it's well researched. Some stat shit they would have dividing with this thing, maybe for efficiency, and then I don't know. Then we just put that. Then this key, we send it through the key matrix. Reflect key matrix q equals the dot query matrix query. All these will be trainable, I'm pretty sure. And equals so dot value 1. Okay, so we end it. Now what do we do? Now we're here. We can actually take it in step ones, bro. This is step one. So we get it into 8.64 now. Hmm. Okay, this is step one, I'm pretty sure. Step one, okay. Then we get the value. This is all still step one. This is all step one, bro. Then equals q dot transpose 1 in the second one, whatever the dimension is, right? In this, we bring 8 outside. If I'm not mistaken, that's what happens. Perform it. I don't know why I did that. Transpose. Let me see one two. Okay, now we have our correct dimension. Then we do the attention step 2, no? Calculate the score. Now we complete the attention score. That's it. And see, we need to get this part. And this is actually a key. So we need to adjust this key so that we can actually multiply it. So we then do the transpose. Because these two are the same, right? These two are the same. We need to change the last two. So 64 should come here and 10 should come there. So we can do that. Is that here? permit k. So k becomes what is that? Okay. So how did it look, bro? Okay, it looked like that only. Okay. So what do we do? Yeah, adjusted. Why? Because so that we can actually multiply. And we have to change the last two. Then only. And we do multiplication also. So basically it does this 38 times and that it does 32 times. So changes in this. Okay, it does that. Then what is the product? Put this on top, bro. Dot equals torch dot map mul adjusted. Then we have that. This into this. Then we have this. Okay. Now we finished, I think, step 2. Scores. Oh, we haven't even still started this. We still have to compute the scores. And we do the math product also. For the mass, if mass fill pose position of the product matrix and mass positions are 0. Because 0 doesn't give anything. This is, I think, the lowest value you can go with that. There is not none. What you're gonna do is to product equals product dot mass. I think this is, it has this thing, whatever, whichever mask is 0. What are we filling with? We're filling with some float. Actually, put torch of, okay, now I think it is comparable. Float will be torch of float. Internal mine is a very low value. Wow, that's a really low value, bro. Then I think this is step 3 here, where we scale the matrix. Yeah, step 3. Where we divide it by product equals product divided by, I don't know, why don't we use torch dot square the computation, this, it has so much this thing to do under in the back end, bro. It has to use this match dot square root. It has to see which one that is, convert it into a torch dot square root for the computational graph, and then do all this stuff. I don't understand, but I'll ask doubt in back end where to put the doubt, format it. Doubt is why I'm using map package for package and you can stop package. Why am I asking this? Start backend computation more expensive as uh, as to map these Python functions to touch functions to add to the computation. Uh, Now let's format this. Why are you asking? I think we just put this in strings, bro. Oh, that's a doc string. I don't think this will work. We'll see. For doc string, it works. I've never done this before like this. I think I got an error. Okay, let's see. So then, oh, um, hmm, singular dimension. Wait, singular dimension is 8 no? Hmm. Okay, number of heads is 8. Single dimension is so 64 by that's decent. And then we just calculate the scores. There is also scores equal uh, sophomore drop equal and scores equal torch dot. They are not importer functional. What is that function, bro? What did he import it as? He imported as capital F4. Okay. So delete F4. Then we got torch dot macmal, no? And what are we doing? Scores, which is basically query, no, query into key transpose whatever divided by the dimensional square root that into v. And v is still 8, 10, 64. I mean, we must have it here. Though. I think this is not efficient like that. We can't go. Let's see which step are we in, bro? Okay, this is step 4. Wow. Oh, I've been on stream for 1.5 hours, bro. Shit. I don't know if my stream is visible, bro. Let's go. Tell me what, I think this step 4. Step 5 is what Concata. Another. Where we step 5, transpose the matrix and then reshape it back into a 512. Mm. So first we transpose it and then transport it again. So basically, for the concatenated one, goes dot something dot something. Okay, we will get to that. Dot u. Let's use this. Okay, batch byte size obviously. Let's see length of query. Okay, and then self dot dimension into self dot end head. Okay, that's done. Okay, now this has to be contiguous. Shit, my spelling is really bad. Okay, now we have that, right? Okay, original one. And again we transpose it. Transpose 1 comma 2. So basically what this does is does a double transposition. So first from 1064, which is what we have here, to become what we actually do is first we transpose 8, 10 to inside 8, 1 and 2. Okay, then what we do is we multiply those two into this thing. Okay, so what I did was wrong. I mean, same thing here, but what I explained was wrong. First, you actually transpose this. You take the 8 inside and then you multiply it. Man, this is the first time I've actually learned something like this, bro. I think I'll just keep live streaming or whatever I do. Contact equals self dot output concat. So what is self dot output? So basically a linear layer for concating, which is basically, I mean, value matrix and all is all easy to understand. So number of heads into number of single layers, 8 into single layer dimension 64, number dimension, which is it gives you this 32 plus whatever on top gives you a 7 for each patch. There are number of heads, single dimension 52 cos 52. What the fudge? I don't know. Let's see. this? Why are we using all the? Oh, so what is this mask used for? Well, we can do it once we're talking about the decoder. So now let's get a whole as picture base 64 encoded. Base 64 encoded image is like this. Number of tokens, embedding size, it's query, this is key, this is query, it's the same. Oh, it's already here. Wait, okay, it goes here. This is the softmax to get attention, and then you get that. So this is basically our embedding matrix. Now let's go into the encoder. I mean, this picture now I can understand it so much more clearly now. It helps. Oh man, this is a really good workshop. I love it. Yeah. I think I'm ending stream. I'm taking a break and then coming back.